video attachment number 3 to the European format Curriculum Vitae or similar. The job is at the root of the shortest path tree. Step towards it. 3, 2, 1, go. From nearly March 2014 to around August 2014, I did some research and development about a method of 3D rendering and contact detection specialized in a type of non-convex polyhedron. Those typically made up by usually curvilinear segments of rods. I started out from an idea already partially implemented into an algorithm in the C programming language years before and tested successfully. Then I went on to develop in the C++ programming language a library for this very language which support fully the creation of programs similar to Google Maps or other software of this kind, but entirely three-dimensional, with full support for a multi-level network of roads, that is, underpassages, high passages, and normal roads, all these things without any particular limitation, including also the possibility to have in this network curvilinear segments of roads, of course, and also segments which have a variable width along their path, and possibly also variable lateral steepness along their path. The fact of being three-dimensional would not be very useful if it could not be adapted on a terrain. In fact, terrain and the fact that the network of roads is somehow fit to stay above the surface of the terrain is inbuilt. Besides the rendering and contact detection system, very light and simple, the purpose of this library was that of combining the 3D rendering of roads with an easy-to-use mouse user interface, with also informational labels overlaid to the three-dimensional scenario, and also some color tracing of various paths, and according to these also set of algorithms for the search of shortest paths and similar things. This library is designed to provide its colorful functionalities at a very low system requirement, and accordingly to this, not only the contact detection performs very few operations to detect the contact, but also is inbuilt an reduction of the level of detail displayed by each segment of road, which decreases as the distance from the viewer increases. Suppose one wants to do a computer program which is somewhat similar to Google Maps or programs like that, for example, but it's fully three-dimensional, and besides rendering actually a basic terrain upon which there is a network of roads. It also allows to a point to a character or a vehicle, whether these are realistically moving or just moving in an essentially cinematic way, to actually walk on the network of roads, where of course the segments of roads can lay on different levels, thus making up a multi-level network of roads wherever this is needed, of course. Two simple functions provided by the library allow to take easily advantage of the powerful contact detection system built into it. Conceptually, if below the point there is no segment of road but there is only the terrain, the height that it gets is that of the terrain locally. By locally, I mean at those x and y coordinates which currently the point has. But instead, if below the point, I mean just watching the whole situation from completely above, there is under the point some segment of road, the height this point will be assigned is automatically the height that that segment of road has, and that's all. Of course, also a segment of road is needed which functions as a sort of trampoline, at least one, which allows to the point to get on a network of roads, while of course it's initially standing just on the terrain. This library provides a set of features which allow to do pretty advanced modeling of almost every type of urban road and also off-road track. But of course, these advanced features are based on an advanced usage of basic and simple concepts which are not new at all. In fact, this simple idea behind the way this library defines a segment of road is this, explained shortly. There is a parametrized curve in 3 dimensions. This curve is traced from a point A to a point B, which are the starting point and the end point of this segment of road we want to obtain. Well, imagine that at each point of this limited segment of this parametrized curve there is attached a simple reference frame, as I try to indicate this with these 3 arrows. A simple rectangular reference frame. Okay, the center point of this reference frame is dragged along this segment of curve. Now let's take this reference frame and consider only these 2 axes of it, which both are perpendicular to the curve locally. Very fine. In this 2-dimensional reference frame there is a polygon which encloses an area, a simple plane area. Now, this polygon, as this reference frame is dragged along the curve as it goes from point A to point B on the curve, this polygon, which encloses an area, spans a volume, similarly to this way. And this is a volume. we can say that at each point of this curve there is a slice of volume, a slice of our segment of road, whether it be a real road or a road on an architectural design. And in the ideal case, of course, the slices are infinitely close to each other, but we can obtain polygonal approximations of this curvilinear, nice segment of road very well also by just taking slices at finite distances from each other instead of infinitesimal distances. And so we create a polygonal model, a triangulated polygonal model of a segment of road, and so on. One can take as many slices as needed. This was a short description of the most basic situation. It's easy to progress anyway to more general situations in which imagine that there is an angle with respect to this line. Consider that the polygon stays in a reference frame which is similar to the original reference frame but rotated by an angle alpha here. And imagine that this angle alpha can vary as the reference frame is dragged along this path. And so we can define segments of roads whose lateral inclination changes along its path. According to this, of course, we can progress even further by allowing the width of the road to vary along the path and other things of this kind. Of course, in this example I have used a rectangle as polygon, but it could have been any two-dimensional polygon. For the purpose of this presentation video, this should be enough to appreciate most of the features of this library. It allows to do modeling of typical urban roads. Some examples are here. Simple road modeling where there is no lateral inclination and no variable width. These are some examples of things that can be done by advanced modeling where only the width of the segment of road varies along its path. Of course, it can be asymmetric since we can define a width at right and a width at left. So all typical connecting pieces of road can be comfortably defined. There are some situations where it's necessary to have at the same time variable width and variable lateral inclination. A typical case are connecting segments of roads which allow to go from a steepy segment of road into a typical parking place, which usually, of course, it's plain. By allowing to use more complicated polygons, we can define, of course, also special segments of roads, including highways with their typical shape, or freeways, and also railways and these things. With this library, it's also possible to model segments of off-road tracks, but this is not explained in this short video presentation, because even if defining a segment of off-road track is comparatively easy with this library, it's instead rather difficult to put it to insert it in a more roughly defined terrain in a meaningful way. Synchronize to. This library allows easily to put into a computer program featuring some kind of virtual environment almost any type of typical urban road system, road network. But of course, being the contact detection system so lightweight in terms of operations it does to achieve to find the contact point, it must of course have some limitation, because the procedure to find the contact can be so lightweight because it operates only on a limited range of situations. Very fine. Even if this doesn't limit the things that can be done with this library, it constrains to some rules which have to be followed while designing the network of roads which will feature in some computer program being done with this library. Okay, each segment of road featuring in the environment must satisfy the following rule. Stated very roughly, if we are looking at a segment of road from above, it cannot turn more than or equal to 90 degrees. It can only turn less than 90 degrees, either plus or minus, with respect to the direction of starting. This, of course, doesn't depend on the orientation. The rule is so simple, very intuitive. Stated in a more involved way, but also more general, we have our segment of road and we are considering only its axis, which is a piece of a parametrized curve. Of course, it has a tangent vector to it at the starting point and at the end point, even elsewhere, everywhere of course, but we take the tangent to it at the beginning and at the end of this segment. And we call them tangent 1 and tangent 2. And the rule that each segment of road must satisfy that the dot product of these two vectors must be greater than 0. Very fine. Now, I'm not a big guru of using spline curves and those things. In fact, in this library, a segment of road can be defined in two ways. One, thanks to 3 points which are interpolated polynomially, one interpolation occurring for each coordinate. Or the other way is to use 4 points, but of course there are some rules to follow here, because 2 of the 4 points must stay very close to the start point one and the end point the other, creating a sort of spline curve. It's similar but not the same thing. Okay. Synchronized 3. If one needs to define some more complicated segment of road, which doesn't satisfy to this requirement, well, it's sufficient to split it into any number of simple segments. Simple, I mean those which satisfy to this rule. They're also visually very simple. And once, for example, let's say complicated segment of road occurring on a map, which we use as starting environment, compares as a single element, once we have splitted it into these kinds of segments, we have to remember to add to the network the nodes which we have added through this operation of splitting, and we also have to add the connecting edges to the very network. One last thing to observe is that there isn't any limitation to the width of a segment of road, so even an entire parking building can be modeled as sum of segments of roads in this fashion. This is a little bit weird, but this is very important to know how to use best the available features. As last thing, unintended intersections of segments of roads should not happen. I mean, where there is an intersection, it should be because there is a node of the network. Unintended intersections can happen in a random generated scenario, of course, and you will see some of these in the example I show, but of course these are unintended situations, and where there is a multi-level network of roads, one should be careful that two roads which should run on a different height, they effectively run on a different height, otherwise they may happen to cross each other in a point where actually there is no node of the network. So we have a terrain, and upon it we have a network of roads, which is automatically by default made to lay as well as possible on the terrain, so that no segments of road occur below the level of terrain, and similar undesired effects don't happen. Now, the last thing to say is, well, how to define the network of roads. Since with this library we want to do something similar to a road map, and in fact our starting point is, I assume, always a road map, we have to start from that. A road map can be defined as or considered as a network of points connected in a way to create a graph. A graph is made of a set of points, which are the nodes, and some segments, which connect pairs of nodes. Between a single pair of nodes, at most two segments can occur, and one of these segments leads from one point to the other, and the other segment, if present of course, does the same thing but in the opposite direction. In fact, on urban road networks we have some segments of roads which are unidirectional and allow to go here or there, and there are bidirectional segments of roads, and a graph is essentially this. To avoid confusion, it's in place to observe that we specify that a road map is essentially a graph kind of network, because there exists also another type of network mainly used in defining electronic circuits, which is essentially still made of a set of points, but between a pair of points an unlimited number of segments can occur which are distinguished. This kind of network is called a netless type of network. So I hope we have resolved all possible ambiguities, and we can say last how to import a graph obtained from a roadmap into a program made using this library for the C++ programming language. Well, there is sufficient to be a text file which lists all the triplets of coordinates of each node occurring in a network of roads, and another text file which reports a so-called connection matrix, which is simply a set of n lines in a text file in which each line of text has n numbers, but these numbers can only be 0 or 1. So that's very simple too. The numbers occurring on the diagonal of these square matrix are not taken into account in this library, even if theoretically non-zero elements on this diagonal have a meaning, and they are, let's say, special nodes which allow to go from themselves to themselves. Typically a circular segment of road would be such a kind of special node, but it's not very meaningful for practical applications for which this library is aimed at, because in real networks of roads usually a circular segment of road occurs as a combination of smaller segments of roads which put together form a circular segment, but usually the circular segment has some forks, and that's why really circular segments of roads are not meaningful. This ends the discussion of how to use this library, as much as it was possible to illustrate it roughly in this short video presentation. But of course, one last thing remains to say, a very concrete aspect, and it is this: in most cases a roadmap, even if it occurs digitally, is more a sort of image rather than actually a definition of a graph, as I have tried to deline it shortly a little bit before. But in order to import some way a sort of, let's say, approximation of what a roadmap tells us about a network of roads occurring in some real part of the world, or in a video game, or just a virtual reality environment, then we must convert this map in a graph kind of definition, even if the roadmap is in the form of just an image, or a vector graphics image, which anyway is still, from our point of view, the same thing, an image. And how to convert it into a graph? We have to identify somehow each node, and we must then find out how to connect these nodes to obtain something which is very similar to the roadmap from which we started, ignoring in this stage completely the width of each segment of road, and coping with those cases in which we have a carved segment of road by just picking some points, laying along it, and just connecting the points with edges. This video is not the place to explain such a conversion procedure. but said very roughly, at each intersection occurring in the roadmap, whether it be a T-junction kind of intersection or a cross kind of intersection, well, we can roughly say that at each such intersection there occurs a node point which will feature in our derived network. And of course, wherever there is a road which connects somehow two of these points, we must add an edge to our graph in the connection matrix. And nearly that's all. I know that's not a very scientific definition, neither provides an algorithm for doing this automatically, but I hope at least I have outlined this in a meaningful way.